Of Supernova Week. I'm going to show you a little bit about how Type 1a supernovae that we studied last time are used to find distance in the universe to very, very distant objects. Then we'll talk about large mass stars, which form Type 2 supernova. And then there'll be some reading homework, little extra reading in the textbook. So let's get going. Have your clicker ready. Last time we talked about supernova type 1a, which are detonations of white dwarfs, and just a few other things to comment with you about that. The range of mass for the star that will lead to a white dwarf and then possibly a supernova detonation, type 1a, if it's in the right conditions, is about 8 solar masses. So, you know, our star might become a supernova detonation eventually. So that means on this theoretical diagram here, from about the black arrow down and to the right. Now those little red ones, it's going to take forever for them to maybe get to the stage where they can go into supernova. But up there at about 8 masses, the age or the lifetime of those babies is fairly quick. And we think that we've seen bunches of type 1a supernovas, you know, various places in the universe. And just to reinforce, the problem is that, you know, eventually the hydrogen fusing into helium is going to build up enough helium that it's going to start it won't be producing enough fusion, you know, hydrogen fusion to keep the star stable. So the core will contract, and as it contracts, it gets way hotter, and then you start fusing helium. And under, you know, various size stars, if you have enough mass, you'll also start fusing stuff like silicon and even iron. You know, so those are exotic fusion reactions, and what that leads to is instability in the star itself. It'll expand and contract, and you know, basically leads you to red giant status. The other thing that we talked about last time was that instability in the, you know, red giant, you know, starting off, you know, like when it goes from carbon fusion to silicon fusion. Okay, that's gonna, you know, that's a transition that might not take very long, but it leads to instability, and you'll blow a few of the surface layers. That's what we call planetary nebula. And remember, they're not planets. They were reminiscent to some early astronomer, I'm sure you could look it up, who thought they were planets, but they're actually not. We looked at a few of those. Now, the white dwarf, after you blow the surface layers to kingdom come, the white dwarf is what remains. And the size of a white dwarf, as I mentioned last time, is maybe about the size of the Earth, approximately. So all the mass of a star, or a big fraction of the mass of a star, crammed down into the volume of Earth. This is really, really dense. And just as a side note, the size limit of a white dwarf is 1.4 masses of the sun. All right, so if you're, you know, if you blow those surface layers and you've got more than that, other things will happen. But if you've got 1.4 or less left over after you blow the surface layers in planetary nebulae, then you're going to, you know, have white dwarf. And as a side note here, I'll add one more thing. And this is, I probably should have put it in the notes, but let me add it verbally. The white dwarf is not undergoing fusion. It's really hot. but it's not hot enough to do fusion. It doesn't have enough mass to compress it all the way down to start fusing some more stuff. So you might say to yourself, well, Dr. B, I thought fusion is what keeps things from collapsing. You know, the hot thermal outward pressure balancing with gravity. And the answer to that is yes, if it's fusing. But in a white dwarf star, you don't have any fusion. And so it's really hot. But what supports it against collapse is something called, and I'll give you this as a vocabulary term. You can read about it in your textbook, electron degeneracy pressure. White dwarfs are supported against further collapse by something called electron degeneracy pressure. It is a quantum effect. It's very fancy, but it's basically the quantum. It's if you've ever heard of the quantum uncertainty principle, Heisenberg's uncertainty principle, it's basically based on that, and that is that you don't like to have quantum particles have to occupy, can only occupy certain regions of space, and otherwise they exclude everything else. And so it's so they effectively, and it's a quantum effect. It's not a thermal effect. Okay, it's like trying to crowd people into a classroom. You know, if we could probably crowd about 1,000 people in here if we had to, but it would be elbow to elbow, and we might break out in fisticuffs if somebody says the wrong thing. Okay, but eventually nobody'd be able to squeeze in on the doors, and that's the same kind of thing. And it's a quantum effect. And the quantum physics of it is very difficult, so we're not going to go into that. But it's a quantum effect, electron degeneracy pressure. That's basically overcrowding. The electrons will not permit any more overcrowding. All right. Now, if it's got a binary star system companion, and if the other one, if it's close enough to lose some mass, and the mass spirals around the white dwarf, we saw a photo or an artist's conception of that the other day, then it's possible for the white dwarf to accumulate kind of get crusted over with stolen mass from its companion, and when the conditions are right for that, bam-o, you get a type 1a supernova. And as a result of that supernova, you get a lot of stuff all the way up in the periodic table. All right, so here's the left-hand side of the periodic table, and the hydrogen up at the top left, and lithium and beryllium. Those are fused together in stars, but the other stuff, not so much. So here's the other side of the periodic table. Let me just kind of shrink it down. All right, so supernova is what we think type 1a and type 2, which we're going to study today. Those are how we think the abundances of everything above iron in the periodic table come to pass in our universe. All right, now here's a picture. Remember, we did this one last time. Here's the white dwarf over here, and there's all this stuff being stolen off of its companion star, and it's kind of swirling around. And because most times there's a little bit of angular momentum, there's a little bit of spin for these objects, and you'll form an accretion disk that's going to spiral down into the surface of the white dwarf. And here's the kind of this generic companion over here, which usually is maybe a red giant star of some kind, but it doesn't have to be that if it's close enough. So now, when I said that the surface of the white dwarf, the white dwarf is, if it's by itself, that's it. It's not going to. It's just going to eventually cool off into a brown dwarf, and then on down, to zip zap. but if it's got a companion, it'll get crusted over with mass. So here's a diagram, a circle, a white dwarf. Now, when I say that it gets crusted over, now check this animation out. Here it comes. All right, so that red stuff is from, I made it red to represent the red giant star companion, okay? And so now over here you've got some, and it's not going to be perfectly symmetric. So just kind of scribble in a little bit over here on the left, maybe a little bit down here at the top, bottom, but over here, that's where we got a lot. So it might not necessarily be perfectly symmetric as it accumulates matter into the crust, into the very surface, and gets crusted over. But when it does, kablooey. You know, so it might start on this side. And if that's what happens, then you get an oblong explosion. You know, it won't be perfectly spherical. All right? And it'll be spinning, you know, so it just depends. But anyways, it's going to get crusted over, and it's the crust that starts it. And then the whole supernova proceeds from there. Now, another thing that I mentioned last time was the cosmic microwave background, CMB. And I told you a story about how, you know, when I was in grad school, they found out about it, and it was very exciting. Stephen Hawking was there and everything. Now, you may say to yourself, well, Dr. B, what is that, like, 1980s antenna array doing up there? Well, back in the 1950s, the telephone system developed microwave antenna repeaters, they call them, microwave antennas, to transmit long-distance telephone calls and everything else. So when you were, you know, like, you know, 30, 40 years ago, 30, 40 years ago, when I was your age, sonny, you know, when you were listening to, like, some news reporter in Los Angeles reporting on a baseball game or whatever it happened to be, and you were in New York, that message came through these microwave, or maybe a satellite hookup. But you could tell, you know, a satellite hookup, you know, the reporters always have a little, like a 2-second delay. You know, the anchor man will ask a question, and then the other guy's looking at the camera for 2 seconds, and then he replies. That tells you that you're on a satellite. But these ones were pretty much instantaneous. Here's another picture. So you can see them, you know, the Bell telephone system, which predates most of your guys' lives. Verizon, AT&T, what's some of the other, Verizon, AT&T, no, not Sprint. Sprint was its own network. Sprint was separate from AT&T and the Bell system. But a lot of the current cell phone companies used to be part of the AT&T Bell system. And so the Bell system was the outfit that designed and developed and produced these, because it was their system. So all these, and you still see them around sometimes. You know. Now here are these guys, Wilson and Penzias, up in New Jersey. It's kind of a posed photograph. These are the two guys that discovered the cosmic microwave background. And you can see in the background of this photo, you can see a gigantic microwave antenna. Now, they designed that thing not for telephone calls. I mean, they knew how to do good ones for telephone calls, you know, mountaintop to mountaintop, et cetera, but this one was actually designed for astronomy. And what they were hoping to do was aim it. You can see there's a wheel, and you can wheel that thing around on one single axis, and then coupled with the rotation of the Earth and the orbit of the Earth, you can hit every part of the sky, or observe at radio frequencies, they were hoping, every part of the sky, right? Because they wanted to do radio astronomy. And we've been doing that for a long time, since the 40s. So this is back in the 60s, all right? And you can see they're wearing 60s clothing, all right? And the problem was they're getting this big, and they work for Bell Labs. All right, so Bell Labs is developing this astronomy tool, even though they're the phone company. They did a lot of basic science back in those days. They don't really do that much anymore. But in those days, Bell Labs just did a lot of scientific things, like lasers and stuff, silicon, microchips, all the things that you use constantly now were developed at Bell Labs. Anyways, the problem was they designed this thing, this big, so they were really getting a lot of radio so they tune it to different frequencies, and they're listening to AM radio, and then to another frequency, and they're listening to FM radio. Or if that's if they're pointing it at New York City, which they could do probably from that location. But so what they were trying to do was aim it at the sky and get extraterrestrial radio frequency. But the problem was, they're checking all their different just like a radio. You have different radio stations you tune it to. And what they found was that down in the microwave region, they were getting a transmission. They were getting noise. And no matter where and they said, oh, well, this is, some microwave source out in space. But they aimed it at every point in space. They couldn't get rid of it. So they dismantled the telescope and they went and cleaned everything out. They found some pigeons in there, and you know what pigeons leave behind, a lot of stuff. And so they cleaned, they took the pigeons to another location, cleaned them out, and they're still getting it. So they thought to themselves, all right, what the, I'm getting it in all directions. I know it's not my machine. So they figured out, oh my God, this is the universe itself. The sky itself is buzzing at this particular set of frequencies. And when they mapped out the intensity, this is what they saw. A black body spectrum. It's actually in the infrared and microwave, for which the temperature is very, very cold, 2.73 Kelvin. Now that's way cold. We're at about 300 Kelvin, our body temperature. So we're giving off infrared. Right? And this is really cold, but it's still considered infrared and microwave. And no matter where in the sky they pointed it, they were getting this excess energy. They thought at first it was noise from some transmitter in New York or whatever. It wasn't that. It wasn't their machine. It was the universe itself. And everywhere they looked. And so what they figured out was, this must be the light from the Big Bang, 14 billion years ago now, we think, that's still streaming through the universe from all directions. But now, and here's how you want to understand this. The Big Bang shed its light that streamed all through the universe after a few 100,000 years after the Big Bang. Before then, it was still so tight, all the light was still captured in the Big Bang. But eventually, it expanded and cooled, and all the light just started streaming off. And the entire at that time, the entire sky looked like the surface of the sun. But as the universe expands, if you expand something, it's going to cool, just like in your car engine. The piston moves up, the interior of the cylinder cools, and then you got to put in more gasoline vapor and reignite it, and you get it to keep going and stuff. All right. So as something expands, it cools, and we call it the photon gas. So about 400,000 years after the Big Bang, a lot of photons just started streaming from all directions everywhere in space. And if they were at several thousand Kelvin at that point, and they've now expanded and cooled to this temperature, 2.73. All right, it's very, very uniform. But we've now been able to measure very, very small variations in the temperature. And we got a couple satellites up there, the Wilkinson satellite and the Planck satellite. This is a Planck image. This is figure 4 from chapter 29.2. So if you listen at these wavelengths in microwave, and we have to do it from space now to get really good precision. This is what you see. You see dark blue, you see hot red. Those are temperature variations. Right now, you can't make a picture of that, but chapter 29.2, figure 4, yeah, you can look it up and read about it. Microwave background. So to a physicist like me that studies the Big Bang and stuff, early universe, we call it, we look at these temperature variations, and what we do is we associate them with pressure variations and density variations. So a little more dense, you got a little more heat, a little more pressure. Now these are very small fluctuations. But those fluctuations that you see here, eventually, we haven't figured out exactly how it works, but we're working on it. Those fluctuations, the blues and the reds, eventually formed galaxies. You know, if it's a little more dense than somewhere else, it might form a galaxy, or, you know, might merge to form another galaxy. So what you're looking at here, pressure, temperature, and density variations, you're kind of looking at weather. A weather map from about 400,000 years after the Big Bang. And my wonderful students, that is about as far back as we can look. We can't look back all the way to the Big Bang, you know, time t equals 0, but we can see this for sure. And from this, we can figure out, well, what was happening just before this, you know, before this stuff, you know, and now we're trying to figure out what happened after this. So anyways, cosmic microwave background radiation, very, very big topic and really interesting. You can read more about it in chapter 29. All right, let me give you a clicker question. Let's double check your understanding of last time. Do you recall anything about the type 1A supernova? Concept number 1. How much of the white dwarf is actually left after the type 1A supernova? Go ahead and vote. Try to remember that kind of September. I don't know any more words to that one. Did you ever hear that song? Try to remember. All right, 30 seconds to vote. You're going to look back in your notes probably. Oh my goodness. Looks like nobody took notes. Go unclick that other one there. Yeah, this one. For now. Well, you can click it back. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Show them this is the screen of shame. You guys, you're flailing. Just, you know, Yeah, go ahead back, and you can grade it. Zip, zap, zobo. Yeah. And that's the whole thing about a type 1A supernova. And that's why they're so useful for us, because the entire thing gets zipped and turned into a big, huge explosion. So zip, zap, zobo. And that leads us to why they're useful. Something we call, something that astronomers call a standard candle. All right, now let me go through the logic of that with you. If every star were a 60-watt bulb, then its apparent luminosity here on Earth would tell us its distance. Or, if every star was, 10 to the 27 watts, slightly more watts. But I mean, if they were all the same, but if they were still at their current location, so if you went around and every star replaced it with something, a 60-watt bulb or 10 to the 27-watt bulb or 10 to the 27-watt star, then whatever luminosity you measure on Earth, and that would be an apparent luminosity, would correlate directly to the distance. All right? And so we don't have that, but if it was the case, then we could, figure out, just measure, with our light meter, all right, so much light that correlates to so much distance, so many light years, so many thousand light years, and stuff like that. And, you have to use trig, and you have to use logarithms and stuff like that to do it, but you could do it, all right? Now, we're not going to do any calculations like that, but the logic of it, yeah. So if you had every star the same brightness, the same intrinsic brightness, then the only variation that would matter to their apparent brightness is how far away it is. I mean, if they were all the same distance too, then they'd all look the same. But if they're at different distances, the apparent luminosity. So if you had 10 stars, 10 of the 27 watts each, and 5 of them were at 10 light years, and 5 of them were at 100 light years, all you have to do to measure the distances, get the apparent luminosity. And then, like I say, do a little trig and a little bit of logarithms, and you get the distance. Now, we don't have that with stars, but we do with type 1A supernovas. And actually, there's a few kinds of stars that we can use as standard candles. Okay, part one, a 60-watt light bulb, that's the idea of a standard candle. 10 to the 27 watt, if every star was a 10 to the 27 watt star, that's a standard candle. Now, type 1A supernovas, yeah, we can get them. We can use them. Because the reason for that is the white dwarf mass limit is about 1.4 times the mass of the sun. So every time we see one detonate, and we can tell type 1A apart from type 2, which is a completely different process. That's a core collapse. But type 1A is a white dwarf star detonating, and those only go up to about 1.4. And so we can use that and say that every type 1A is about the same intrinsic luminosity. So if it looks dimmer, if two supernovas, type 1A, if the spectra tell us that, okay, we got two type 1As here, and one of them's further, it's going to be dimmer. If it's closer, it's going to be a little brighter than the other one, right? That's a standard candle. And the apparent, the proximate luminosity, and it dims off after, over the course of weeks and months. And we're going to look at a type 1A here in a second. It's about 5 billion times as luminous as our good old SUN. All right, so knowing that, that's like our 60-watt bulb. Now, the problem is we don't see a whole lot of them. We don't, sometimes they're obscured by the center of a galaxy, but they'll outshine an entire galaxy if you're looking at the galaxy from the right direction. So it's pretty amazing, really, if you think about it. And the good thing is they're so bright that they're visible most of the way across the visible universe. So if we, sometimes we can't even see the star, or we can't even see the galaxy, but we can see that supernova blazing out, and then we can figure out how far away its galaxy is. Okay, and that's how we know. That's another reason, another way in which we can find out that the universe is expanding. Because all the galaxies except the very few near us, like Andromeda and our local group of galaxies, a few galaxies, then we all orbit each other and stuff. But outside of that, the further you are away, which we can tell by, for instance, type 1a supernova, the more redshifted all your spectra are. So your H alpha lines are deeper into the red. And your H beta line is in the lecture hall, in the lab, is kind of aqua, tealish color. It's maybe a little bit more green or even yellow, depending on how big the redshift is. Right? So we see every galaxy in every direction redshifting. They're all moving away. And the further they are away, the more they're redshifting. That means the faster they're going. So that means that if you run the tape backwards, eventually they are all in one place. The Big Bang. Da, 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 da. So that's how we know. When we saw the universe expanding, somebody said, well, you know what that means? It means that if you reverse the film and move it backwards in time, they were all back together in one place. And that's when they started thinking about the Big Bang. Anyway, so type 1a, standard candle, very useful. And we have a few other ones. There's a couple kinds of stars. If we can see them, then we can know the intrinsic brightness. But that only works, it doesn't work as far out as type 1a. Type 1a supernova, you can see them just about anywhere. If you have the right angle on it and stuff. And if you're looking. Some guy here, I think in 2017, was photographing some galaxy, and he just happened to bag a supernova. It was really nice. So then he puts out the alert, and then everybody's starting to look at this galaxy, and they're charting out the amazing, at every single wavelength you can imagine. They always want to know everything about these supernovas. All right, so that's for what we call low mass stars. Let's look a little bit further up the main sequence now. We looked at this one last time, zero-age main sequence. What we want to do is look at stuff up here at this end. Now, this stuff has a short lifetime. And so they're going to go supernova more quickly. They're going to go through all their exotic fusion reactions. But if they're at if they're more than about 8 times the mass of the sun, they're going to undergo something called a core collapse. And that's the main topic of our lecture today. All right, now here's a picture of Cassiopeia A. All right, and this is a multi-wavelength image. And this is from the journal Science. I have the citation for it here in a couple slides. And actually, that looks pretty good. Okay, there's the citation for it in pretty small letters. Now, this is a supernova. Now, what they did back in the 50 years ago or more, they found this in radio frequency. This is one of the brightest radio frequency structures in the universe, okay, so far that we've found. So everybody started looking at this, then they started turning optical telescopes to study it, and now this is a composite of X-ray and infrared. So this is not really visible wavelengths here. So this is false color, right? And the reddish stuff is, go ahead and make a note. Red is from infrared. And that was measured out in California at the Palomar telescope. And then a satellite called Chandra, Chandra, it's an X-ray observatory up in orbit, measured the blue and the green, and that's X-ray from really, really hot stuff. So let's take a look at this in detail. This is also, you can also look at figure 2 in chapter 6.5. They've got a little blurb about it. All right, as I mentioned, it's very bright in the radio wavelengths. This is a combo of infrared and X-ray. And you guys, this one, they're mostly looking at iron. You know, these observatories are tuned to look for iron spectral lines. Now, we didn't do any iron lines in lecture on the first day of school, but we could have. You know, maybe, I don't know. I don't know how you do iron, but probably very difficult to do, but not if you're a star, not if you're a supernova remnant. Okay? And so they were specifically looking at shock waves, which is where a lot of in the supernova explosion, as I mentioned before, that's where a lot of your periodic table above iron is built up. Now, so they got a lot of iron you know, they're used to looking at iron, but you know what? They also found phosphorus. And there's something special about phosphorus. All right? And they looked at it through diffraction gratings, basically. They checked the spectral lines. And by Jove, by Jupiter, by Gemini, they found some phosphorus diffraction lines. And so here, let's take a look at how they did it. See these little white sticks, the little white straight lines? That's actually the part of the supernova remnant they actually looked at. So what they basically do is they aim the starlight, you know, they aim their telescope at this supernova remnant, and then they aim, you know, they focus it down onto a slit, and they look at this particular strip, okay? And then they get diffraction, you know, it goes through the slit, diffraction slit, and then they get diffraction lines. And that's how these things work. All right, so they have so then they look at the diffraction lines and they know, all right, I'm looking for quantum fingerprints. And they saw the quantum fingerprints of iron, lots of iron. But then when they looked at, you know, and made real precise determinations, they saw phosphorus. They see other stuff too. They could see sulfur and, you know, all kinds of different elements. This was famous. This article is famous because this is the first one where they extracted phosphorus. So here's another strip, and there's one up here. Here's one over here. There's one down over here. One over here. And then apparently down here, they did a couple strips right next to each other. I guess they really want to get that now that's red, so that's infrared. You know, the false color red is the infrared part of their observations from out in California. And then see that little plus sign? Go ahead and take a look at that. See that little plus sign? Come on, take a look. Don't look at your computer. Look at this. See that little plus sign there in the middle? That's the center. That's where they think the actual star was. There's nothing there anymore. All right? But that's the center. You know, all the smithereens are diverging from that point. You know, so in other words, they play it backwards. And we could see this thing move from year to year. I mean, I was looking at a journal article last night. It was kind of cool. They took some, and I think actually, no, I don't think it was this image. But they took some pictures in December of 2003, and then January of 2004, so a couple of weeks, no, I think it was a year apart. And you could see that you know, these smithereens are moving. They change positions visibly. It's close enough. It's pretty far away, but it's close enough and big enough and bright enough that we can actually see these things moving. It's kind of cool. So we know, backtracking, that you know, all the smithereens, all these blast waves, are moving away from that point. By the way, if you look at that, you'll notice a pattern, a visual pattern. And that is all those strips where they were making their observations, they're all about the same distance from the plus sign, the center. So that means it's a shock wave that they're looking at. They're looking at an outward moving shock wave, and it's blazing up a lot of these exotic nuclear reactions. That's what they're detecting. In this case, phosphorus. Okay, so now oh man, I thought I had a quote. The quote is that the reason that phosphorus is important is because phosphorus is necessary for life. You know, phosphorus, sulfur, nitrogen, carbon, oxygen, hydrogen. They think those are the 5 that they think are necessary for life. And up until this point, they'd been wondering, you know, about the presence of phosphorus in supernova explosions, supernova remnants. So they're pretty happy about finding phosphorus. Because you know what, guys? We have this idea. There's life out there. If there's life, it needs phosphorus. Probably. Unless it's a robot, I guess. Anyways. Now, this is a type 2 supernova. And so the type 2 supernova is basically a story about iron, the trouble with iron. So let's look at this. Now, if you go to webelements.com, go ahead and jot that down. It's a periodic table. It's basically an online periodic table. And you can look up iron, aluminum, gold, silver, mercury, you know, any element on the periodic table. You know, look up all kinds of specs. You know, you can look at their spectra. You can look up their melting point, if it's a metal or a solid. You can look up the boiling point, you know, if it's a gas. So now, but what we're going to do is focus on the mass or the weight per nucleon in iron, because it's the lowest of all the elements. And just to review, nucleon is the generic term for either a proton or a neutron. All right? So the stuff inside the nucleus. Now, we're comparing aluminum 27 and iron 56. And so what that means is that's the mass. Aluminum is 13 protons. Iron is 26 protons. But the isotopes have, you know, various numbers. Aluminum 27 and iron 56 are what we're looking at here. So here are the isotopic weights. Go ahead and write these big digits down. 26.981, 5386 for aluminum 27, which you can look up at webelements.com. And then 55.934, 9393 for iron 56, which you can look up at webelements.com. I mean, you can double check all these calculations. All right, so these are two elements in the periodic table. Now, if you divide aluminum's number by 27, you get, and write all these digits out. You're not going to have to memorize them, but there's something I want to show you about. Now, so the mass, the atomic mass unit per nucleon is for aluminum 27 is 0.993162444. Right, write out all those digits. We've got it well measured. You know, the guys in the chemistry department are doing their job for once, instead of stealing all of our supplies and like our monsters and stuff, all the good stuff from the vending machine in the physics department. Anyways, iron 56. So you take this big number down here in the yellow, 55.9349393, and you divide that by 56, you get 0.998838202. All right? So go ahead and write down all those digits. Now, you're not going to have to mesmerize them or anything like that, but I do want to point something out to you. They're both pretty close to 1. You know, if you were going to round them off, you'd round off to 1. I mean, that's how the atomic mass system works. But the difference, there's the difference. Look at the first 5 digits. I mean, that's all you have to look at. You know, the first 5, 0.99931 for aluminum, and for iron, 0.99883. So that's a little bit smaller. And the reason for this is iron is really tightly bound, and we can't fuse it to a lighter nucleus. And if we try to fuse it into anything, it'll be it'll be a heavier nucleus. All right. So we're not going to get any excess energy. We can't break it apart like we do for uranium. You know, you break apart uranium, you get some excess energy. You fuse some hydrogens into helium, you get some excess energy. You know, that's how nuclear reactions, you know, exothermic, you might say. But you can't do it with iron. So iron's got a problem. You know, there's no E equals mc squared energy that you're going to get because of these nucleon numbers. You know, we can measure them in the lab. And unfortunately, E equals m. I mean, you can fuse stuff, but it requires more energy to do it than you get out. And so it's going to be sucking in energy. It's not, you can't run a city or a submarine or an aircraft carrier or anything else with something that sucks in more energy than it provides. So that's the problem with iron. And here's a quote from chapter 23.2. Of all the nuclei, are you getting these chapters down? I'm trying to put in more chapter citations here, you guys. Of all the nuclei known, iron is the most tightly bound and thus the most stable. And so that's basically, in a nutshell, that's the trouble with iron. So once you've got a star and it's moving off into red giant or red supergiant land, and it's doing these exotic fusion reactions, and so it's cooking up oxygen, it's cooking up silicon, and you know, it's cooking up magnesium nuclei and all these exotic nuclei, and it's doing it pretty quickly. But once it gets to iron, it can't cook up anything with iron. So again, just like with a white dwarf star, no fusion. You've got this ball of iron in the core, and that's all you got. You're not going to get any fusion out of it. So what happens? Stops producing extra heat. It's still hot, but it can't produce enough outward pressure to be stable against gravitation. Let me repeat that. Once the core of your star is iron, no more fusion allowed, everything collapses. Everything above the core is going to start collapsing down. And that is your catastrophic supernova. Type 2 core collapse supernova. Now this one is called, this image, one of the most, and this is actually from your textbook. I can't remember which image this is. I should have put it on there. I'm sorry I didn't. This is called the Crab Nebula. And this is a supernova that I think it was 1054 AD. And this one they did make a note of in the, I think the Chinese are the ones that made a note of this one, Chinese observers. Okay, so this is type, as before, visible halfway across, most of the way across the visible universe. Now, we've already done type 1a, and let's do type 2. And actually, type 1b and 1c are also considered core collapse, but I'm going to mostly mention type 2. Okay, so we have a large mass star, iron core collapses, and when that happens, everything crushes down and basically bounces off the core. The core can't be compressed anymore. And you get this outgoing shock wave. So the inner layers above the core collapse onto the core and they shock out. But there's stuff above that coming in. So the shock wave outgoing hits stuff that's coming in and blazes up all kinds of thermonuclear reactions. All right? But at the core, that iron is now in a world of trouble. And it starts to collapse. It can't hold itself up. And it becomes a ball of neutrons. A neutron star. Possibly a black hole. We'll get to that in a second. So let's look at some more type 2 supernova. Here's another type 2 supernova image, a remnant. Here's a famous one. Go ahead and write this one down. SN 1987A, type 2. And this is a supernova that they observed in 1987. This is the first one. They see a few every year, I guess. So they name it by the year. Now, this is going to, I want you to look at this movie. I'll try to look at it a couple times. Look at this movie. All right? Here's the, let me see if I can start it. All right, now here it is in 2009. Now this movie, oh, is it? Oh, okay. It's playing on the screen. See how the date's changing? And see how the brightness changes? And you can see little knots. All right, let's go back. Here it is again, 94. Look how it brightens up, 96, 97. We've been following this one for decades. See those knots? And now they're getting really, shock waves. It's blazing it up. 2007 and on up to 2009. Let's take a look at it one more time. Here we go, 94. This is about 15 years. See, it dims out there for a bit, and then another shock wave arrives. Bammo. And notice that it's not symmetric. Those knots, they're not perfectly symmetric with, some other knot, on the other side of the ring. All right, here's what they look like. Now, those were Hubble Space Telescope images. This is what SN 1987A looks like in X-ray. So the image on the left over here, let me get my cursor over here. This bluish one, that's false color X-ray from the Chandra Observatory. Completely different. Notice that? It just looks like a ring-shaped blob in X-ray. But in visible, Roy G. Biv from the Hubble Space Telescope, you can get details. And those details change over the years. That's how fast these things are changing. And that doesn't even include the internal. This is just the shock wave. This is the remnant here. When they were actually looking at the central object, before it expanded a whole lot, that's the center of this picture. Okay, so the periodic table. Look at that. That's it. Periodic table for somebody. And this is in another galaxy. Do you remember which one this one's in? It's in one of the two Magellanic Clouds, which are little dwarf galaxies orbiting with us in the Andromeda Galaxy. I think it's large LMC, Large Magellanic Cloud, if I recall correctly. So here's some specs. Yeah, it's Large Magellanic Cloud. It's about 168,000 light years away. That's pretty far for us, but for the universe itself, you're talking billion. You know, the furthest galaxies we can see are many billions of light years away. Not just, so this is fairly close. All right. Now, it's interesting because in 1987, they picked up a neutrino burst. Now, I'm going to tell you a little bit about neutrinos here in a second. A neutrino is a small neutral particle that is ejected or absorbed in nuclear reactions, and it travels at approximately the speed of light. It's not exactly massless. It has a mass, but it's very small. But it still travels at, like 99.999% of the speed of light. So it's very fast. And we've been able to measure its mass. Back not in 1987, they were trying to determine the mass of the neutrino. They thought it might have a mass, but they hadn't done it. But they did. So they have all these neutrino observatories. Basically, they're tanks of heavy water, purified heavy water, which this one was. And so it's water with a lot of deuterium atoms in it. Okay. And those will they'll absorb neutrinos that are blazing past and cause a small nuclear reaction in the water, and we pick that up as a little flash of light at a certain wavelength. They also have a famous neutrino detector in South Dakota in a deep gold mine. And they tend to have these things underneath the surface of the earth, like inside of a mountain and stuff. And the one in South Dakota in the Home State gold mine is filled with some kind of dry cleaning fluid. I don't think it's carbon tetrachloride, but it's some other. And that particular chlorine carbon compound also has a high probability of capturing a neutrino and producing a flash of light. Anyways, so they're looking at this thing invisible. They're looking at it in X-ray. They're looking at it in every possible way that they can. Infrared, radio, and they even picked it up in the neutrino detector, the Kamiokanda neutrino detector in Japan. The shock wave moves out, we think, at about 100,000 miles per hour. That's pretty slow. And now, it's slowed down, but, I'm sure it was pretty fast in the first few minutes. Okay, so here's a picture. This is from your textbook. Circumstellar gas is the outside the black area. And then the forward shock wave is the purpley area. So when that forward purpley area hits interstellar gas, it converts it into, some other nucleus, or it can convert it into some other nucleus. Okay, and then there's the shocked ejecta behind that. So this thing ejects matter. It has catastrophic ejection of the outer layers, not like a planetary nebula. It's catastrophic. But the following shock waves from neutrinos and from photons will shock all that stuff and do these exotic reactions. So SN 1987A was a blue supergiant. It wasn't red, it was blue, we think. And the ring is, right now, it's about 1.32 light years across. So that's pretty, so 1987, 97, 07. So that's about 30 years. and it's about 1.32 light years across. So we're tracking it, trying to figure it out. Now, I mentioned neutrinos. And I mentioned that the ball of stuff left afterwards, after this kind of detonation, iron core collapse, is a ball of neutrons. All right, now here's go ahead and make a diagram of this. The red one over here, this indicates a proton moving to the right. And this blue one over here indicates an electron moving to the left. Now, when they get close enough, they exchange a W minus. Now, that's a subatomic particle. It's a virtual one. It's moving horizontally. So, and the outgoing products of the reaction are a neutron here, and over here, a neutrino. Now, this little curvaceous V over here in gray, in the upper right, that's Greek lowercase nu. Nu. So it just kind of looks like a V. But it's a nu, and it's outgoing. So when the iron core, so the protons and the electrons in the iron core, they're smashing into each other at a big fraction of the speed of light. So they're really booking. And when that happens, this reaction can occur. And the output of the reaction, they smash into each other, and you get a neutron out and a neutrino. Now, the neutrino will pass through anything, just about. It doesn't, it's neutral, it's very small. You know, neutrons, we can capture neutrons fairly easily. Neutrinos, the neutrinos coming from the nuclear reactions in the sun are pouring through your body right now. You're drenched in neutrinos. But they're neutral, and they're small, and they don't really interact. You know, you might have 1 or 2 neutrino reactions inside your body in a lifetime. Maybe. They just go streaming through you. You don't even notice it. And they go streaming through the Earth. The Earth is pretty transparent. That's why they try to have a neutrino detector down underneath the Earth, so they don't get any stray neutrinos from reactors or anything like that. So they put it underneath the mountain. So the only neutrinos that they get are from stars like the sun or from SN 1987A. Now, those neutrinos carry energy and momentum, and there's zillions of them. It's very dense neutrino output in an iron core collapse. So they form a shock wave too. So the outgoing photons of light, you get blazed by that. You're going to heat up, maybe start a nuclear reaction. And then right after that, the neutrinos are coming along because they're a little bit slower. They're only at 0.999% of the speed of light, or 99.999% of the speed of light. So they're a little slower. So they come right after the photons, and that's another shock wave. More exotic nuclear reactions. All right? Question? No? Okay. So let's look at those core collapse leftovers. In other words, let's look at a type 1A leftover. We've already talked about it. The white dwarf. There it is. Artist's conception. A white dwarf, about the size of the Earth, maybe. All right. And you see down there at the bottom of the diagram a little arrow at a little blip. That's supposed to represent a neutron star. So all right, so you got to have a neutron star at this scale in this diagram is too small to really see. So let's change the scale to the scale of New York City. And that, my wonderful students, is about the size of a neutron star. Core collapse, supernova, all those remnants, those ejecta go outwards. We saw that movie. But at the middle is a neutron star. And the Crab Nebula has a famous neutron star because it also is a pulsar. Here's another one. Let's take a look at Orange County. How big would a neutron star be? Well, here's Orange County, right? And UCF, here's 408, so UCF is right about here, all right? And where would so if we parked a neutron star near campus, yeah, there it is. So maybe 20 kilometers diameter. So it would fit nicely into Orange County and cover up UCF, but not all of Orange County. That's a neutron star. Now that's the mass of several suns packed into that density. Side note. The neutron star can support itself against gravity by neutron degeneracy pressure. Go ahead and make a note of that. Neutron degeneracy pressure. You know, white dwarfs, electron degeneracy pressure. Okay, that doesn't work for neutron stars, but neutron degeneracy pressure is strong enough. Here's another picture. They think the structure is about like this. Now here's, before we depart, let's do, we're almost done. Let's do another couple slides here. Go ahead and make a note of this name, Jocelyn Bell. And her name, when she was a grad student back in the 60s, she's the person that first discovered pulsars, a radio source, very precise, that had beeps. In other words, it pulsed. It pulsed out a radio like a lighthouse. But she didn't know, they thought they knew, but you know what they called it at first? LGM. You know what that meant? You know, a beeping signal, regular as a lighthouse. LGM, little green men. That's what they first, but now they call them a pulsar. And this is what they think they are. The pulsar is a neutron star, and some of the stuff around it is still hot enough that it can produce electromagnetic radiation. So if it's spinning and you're in the direction of one of these two yellow cones, you're going to get a very regular beep of electromagnetic radiation because it's spinning. All right, so it's spinning like a lighthouse. And so pulsars, now the interesting story about Jocelyn Bell is she discovered it, she figured out what it was, and she was a grad student, right? Just like Jenny. But guess who got the Nobel Prize for this? Her thesis advisor. I'm not going to name him. The only one I'm going to name is Jocelyn Bell, and long may she reign. Now, I mentioned black holes. And yeah, we're going to be studying black holes next week. And that light cone that you see up there, I'm going to tell you all about light cones. All right, so you're dismissed. I'll see you next week for Black Holes Week. Look for some homework over the weekend. Jocelyn Bell, did you know that story?
I didn't, but I like it.
Yeah.
I'm not surprised.
I'll tell you, you know, I'm sure that Dr.